G'day everyone, and welcome to our lesson on series and parallel circuits. This lesson, I think it's best run when there are a lot of example questions going on. So we're going to use these two formulae up here, and of course Ohm's law, V equals IR, to solve for unknowns in a few circuits. So things like current or voltage at different resistors. So first of all, let's talk about series. I'll draw a series circuit up. I've got a voltage source, then I've got the first resistor, second resistor, third resistor. Let's say we're using a 10 volt source here, 4 ohms resistance for this resistor, 6 ohms and 10 ohms. Well, our unknown is the current and the voltage across these three. So the first thing I want to mention, in a series circuit, the current through resistors in series is the same. And that's pretty obvious when you think about it. There's only one wire for charge to flow through. So if we measure the charge flowing past this point per unit time, we're going to know the charge flowing past this point at unit time. It's going to be the same thing. It's going around at an even pace. Let's figure out the current here. We have Ohm's law. We have the voltage. We have the resistance of each of these individual components. But we need to figure out the total resistance, because we know that this applies for each component, but it also applies for the whole circuit. So V total equals I times R total. And to find the total resistance of this circuit, what we basically do is we look at it from the perspective of the battery. The battery doesn't know what's going on down here. All it sees is a big bit of resistance down here in the circuit. So we can collapse these resistors into one. And the way we do that, we say, okay, the total resistance here is equal to the resistance of the first component plus the second plus the third plus any others if we had them. So that's 4 plus 6 plus 10. Our total equals 4 plus 6 plus 10. That's 20 ohms. So from the perspective of the battery, all it can feel is this 20 ohms resistance on circuit here. So the current I is going to equal V total over R total, rearranging here, to give 10 on 20 or 0.5 amps. So the current flowing past this point here is 0.5 amps. If that really is the current flowing through each of these components, since the current is the same for every resistor in series, we can apply Ohm's law now to each individual resistor. V equals IR. In this case, that's 0.5 times 4, or 2 volts. Over here, it's 0.5 times 6, or 3 volts. And over here, it's 0.5 times 10, or 5 volts. And then we also notice, hey, just as we expected, the voltage dropped on the resistors. 2 plus 3 plus 5 equals 10. And that's the same amount of voltage that was supplied to the entire circuit. So we know that our answer is correct there. The most important thing to remember is that in series, since the current is the same, it's very simple to find the total resistance, which is what the battery feels, just by adding up the resistance of the individual components. Let's look now at parallel. Parallel. We'll use a 10 volt power source again, but we'll put all 3 resistors in parallel. We have 4 ohms here, 6 ohms here, and 10 ohms there. and 10 volts at the top. We'll solve to find the current here and the voltage across each of these, as well as the individual currents through here. So the first step is easy. In parallel, the voltage across each resistor is the same. So we can find the voltage across this one, and this one, because they're all 10. That's easy. Voltage is equal to 10. 10, 10, 10. But the current that's flowing here has to split off 3 ways on the way down. So we expect that there'll be a lot more current, a lot more charges flowing around this section of the wire than this section. There's 2 ways to do this. Let's first of all solve it by using the holistic approach and drawing what the battery feels. So the battery feels something like this. It knows it's here, and then instead of feeling these parallel resistors, it just feels a big resistance on itself. So the battery was 10 volts, and it's feeling this RT down here. The way we find the total resistance the battery is feeling is using this formula. 1 on RT is equal to 1 on 4, that's R1, plus 1 on 6, that's R2, plus 1 on 10, that's R3. And this comes to 31 on 60. But we didn't want to find 1 on RT. We wanted to find just RT, so we put both of those to the power of -1, and we find RT equals 60 over 31, which is equal to, in decimals, 1.94 ohms thereabouts. The battery basically feels a total resistance of 1.94 ohms. So to find the total current, we can apply VT equals I RT, rearranging to get I by itself. VT on RT equals I. 10 on 1.94 is around about equal to, now I've used the unrounded version of RT and I got 5.17 amps. So there's 5.17 amps leaving the battery, and that must mean here on this shoulder, and this shoulder here and here and here, but not, I can't take the measurement here yet. There must also be 5.17 amps. Let's find out how many amps are going through this resistor here. Like I said, Ohm's law, V equals IR, can be applied to any individual component as well as the whole circuit. So if we know 10 is V equals IR, 10 is equal to the mystery I here, times 4, so 10 on 4 is equal to I. That's 2.5 amps. So we found I1 there. Now we can find I2, V equals IR, V is the same 10, I is what we want to find, times 6, so 10 on 6 is equal to 1.67 amps. And finally down here we have 10 is equal to I times 10, I equals 1 amp. So we have 2.5 amps going through here, 1.67 going through here, and 1 amp going through there. If you add up 2.5 plus 1.67 plus 1, you get 5.17. And that makes sense because the current that's flowing through here comes out there, meets up with this current here and this current here. So in parallel, the currents of each resistor in parallel do sum to the total current here. Whereas in series, we found that the voltages across each resistor sum to the total voltage. So now we've looked at parallel and series in isolation. Let's look at combinations. I'll pop in V equals IR and VT equals IRT. So combinations. Circuits that have both series and parallel elements. Let's draw one. Here is our parallel element. Followed by what we'll call our series element. So it's not that there's anything different about the resistor. It's just the way we've placed it. We've placed this resistor so it's occupying the only track through the circuit, but these resistors are branched here. They're in parallel. We'll still use the 10 volt source. That'll be 4 ohms, that'll be 6 ohms. This will be 10 ohms. Let's figure out the current here, the voltage here, the current for each of these, and the voltage there. So the first thing we do is try and collapse this little bit of parallel circuit down into what we can see, what we can model as a series circuit. So the resistance here for this section, there's some total resistance. 1 on the total resistance for this section here. We'll call this RT. Actually, let's call it R, the total resistance of 1 and 2, this being 1 and this being 2. So R12, or rather 1 over R12 is equal to 1 on 4 plus 1 on 6, using this formula here. Therefore I have R12 comes to 2.4 on the calculator. So what we can model now is a circuit that looks more familiar. We still have this 10 ohm resistor, that hasn't changed, but we can model, or basically pretend, these two resistors in parallel are acting like a 2.4 ohm resistor there. And then we can further pretend that from the perspective of the battery, it doesn't see the two resistors, it sees 10 plus 2.4 using this formula here, 12.4 ohms. And if this is the case, we have 10 volts total voltage, 12.4 ohms total resistance, 10 is equal to 12.4 times I, V equals IR, so 10 divided by 12.4 is equal to 0.81 amps. So if there's 0.81 amps here, there must be 0.81 amps here, and there must be 0.81 amps there. And if that is the case, there must also be 0.81 amps here. So I is equal to 0.81. So this unknown, which I was gunning for, V equals IR, I can say I was equal to 0.81, resistance is equal to 10, so the voltage is equal to 8.1 volts, or thereabout. We're approximating here. If I wanted to know the voltage for these two, I can actually shortcut to it. I know that there's a total of 10 volts across this entire circuit. 8.1 is lost here, so there must have been 10 minus 8.1, which is 1.9 volts available for these two. So V, I think, is 1.9. Another way to solve this is to go back to this approximation, or rather model, and say, okay, if the current really was 0.81 amps, then the voltage across this one was equal to 0.81 times 2.4, which I have here equals 1.94. So a close approximation to what I had over there. If both of these components have 1.9, we'll say 1.94 volts, we can apply Ohm's law to each of these components. V equals IR, so V on R is equal to I. This I value here is equal to 1.94 on 4, which I have as 0.485. And this current value down here, that's in amps by the way, is equal to 1.94, the same voltage over a different resistance, and I have that is 0.323 amps. So I like to call it collapsing. By collapsing the circuit down into something more and more simple, we can solve for, first of all, I like to find the total current, and then we can expand up and, using what we now know, fill in the rest of the blanks along the way. If you're consistently getting problems in series and parallel circuits wrong, just recognize there's only 3 actually critical formulas that apply here. So with a bit of practice, anyone should be able to master this stuff. So to summarize that, if you want to find the total resistance of a series circuit, or even a section of a circuit that is in series, you simply add up each resistor here. But to find the total resistance of a parallel circuit, or a section of a circuit in parallel, you have to use this formula here, which can be actually rewritten as RT equals 1 on R1 plus 1 on R2 ... to the power of -1. That's a bit of a shortcut for the calculator. And you can apply the Ohm's law, V equals IR, to the whole circuit and then to each individual component to solve for the final unknowns.